So today I'll talk about absolute extrema. I'll start with introducing a light problem to give you a basic idea of why we want to do this. Then I'll give you the definition of absolute extrema and then relative extrema. We'll also talk about the related topic of critical numbers, and then I'll show you in general how to solve some simple optimization problems. So an absolute extrema is just some value in the domain so that that value is larger than every other value in the domain. We write that notationally as f of c is greater than or equal to f of x for all values in the domain of the function. Similarly, f of c is called the absolute minimum of the function, provided that it's lower than every other value or equal to every other value in the function. These maximum and minimum values of the function are often called extreme values. They're also sometimes called global values. Now, if you look at these three graphs, you'll notice that some of them have maximums, some of them have minimums. Literally, you can find the absolute max and min as the point on the graph, that is the highest or lowest point on the graph looking at vertically. So in the first graph, you should be able to see that the first graph has a maximum value, and it has a minimum value. While if you look at the second graph, it certainly has a minimum value, but as the graph keeps going upwards, it has no maximum. And the last graph, this graph has a minimum value here on the lower left-hand corner, but it has no maximum, because where it would have a maximum value, there is no point on the corresponding graph. There's no function value that gives you that particular y value, so that every other y value is less than it. So what we need is some way to guarantee that a function has a extreme value, both the max and the min. So we have the extreme value theorem. If a function is continuous on a closed interval, then it will always have a maximum value and it will always have a minimum value on that closed interval. When you are asked to say what is the maximum or minimum value, remember those are the outputs of the function. But we often will report and say the maximum is at the point, the x value, and then the corresponding y value. Or you might use the function notation that the maximum value is f of a, and that happens to equal b. B being the maximum and a being where the maximum occurs. Now all we need is some method to find them. In order to find our absolute maximum minimum, we need to look at a related topic first. A function has a local maximum value at x equals c in its domain if the function value f of c is larger than every other function value for all x that's in the domain and in some open interval containing c. Now there's a similar logical definition for the local minimum. These values are also often called the relative extreme values. Now, just for some observations, these relative extrema are just local versions of absolute extrema. And in fact, looking at this graph, you can see that there's clearly an absolute maximum value and an absolute minimum value. Remember, maximum and minimum refer to the output of the function. It's the highest value and lowest value the function ever gets to. So in a graph, it's just the highest it goes and lowest it goes. But the relative max, there's actually two of them. In each case, it's a relative max relative to the local area around it. And there's actually two relative minimums, one being the left endpoint and one being this lower corner. So notice that it seems that to be a extrema, either a max or a min, you have to be a relative extrema. But the relative extrema can only occur in two different places. They either occur at the endpoint of the domain, as you saw here in this graph, or in the interior. So let's consider this graph and try to find all the relative extrema. They would be the local high or low points in the graph. This is all the points that result in a relative max or a relative min. Now, look at this each point and look at the local area for the graph at that point. You should notice that in many places the slope either doesn't exist, such as the two middle points in the graph, that's where the graph comes to a sharp corner, or at the ends, at the endpoints, again the derivative doesn't exist because the function is not defined to both sides. But there are 2 points where the graph is rounded off, and being a relative max or relative min, it seems like the graph is flat there. So you'd be led to believe that the slope of the graph at any relative extrema either is 0 or just plain doesn't exist. But you wonder, are there other points where the derivative is 0 or where it doesn't exist? And yeah, I actually include them here. These two green points are not relative extrema, and yet the derivative is 0 or doesn't exist. So just because the derivative is 0 or doesn't exist does not mean we have to get a relative extrema. But it does appear that if you have a relative extrema, then either the derivative at that x value is 0 or just doesn't exist. For that reason, we're going to define any value in the interior of the domain where the derivative is 0 or doesn't exist. We will call that a critical number. Notice critical numbers now must be in the interior of the domain, and it must be in the domain of the function, of course. Really quickly, let's go about finding the critical numbers for a function just once. So take this example. If you have the function f of x equals x squared divided by x minus 1, in order to find the critical numbers, there's a simple process. You just find the derivative first, find wherever the derivative is 0 in the domain of the function, and then also find where the derivative doesn't exist, again in the domain of the function. Finally, just make sure you answer the question. So if I found the derivative by using our normal quotient rule, we would get that. I then set that equal to 0. And the only way a fraction can equal 0 is if the numerator is 0. So that would mean x squared minus 2x equals 0. By factoring, that gives you x times x minus 2 is 0, and therefore x is 0 or 2. Those are both in the domain of the original function, so they count as critical numbers. Then you would find out where the derivative would not exist, again in the domain of the function. The only way that fraction would not exist for an x value is if the denominator was 0. But if the denominator is 0, that would mean x has to be 1. But 1 is not in the domain of the original function, and therefore it doesn't count. So there are no such values in the domain of the function where the derivative does not exist. It always exists. To answer the question, the critical numbers therefore are x is 0 and x is 2. Now I implied that there was a connection between critical numbers and local extrema, so let's prove it. If a function has a relative extrema at an interior point C of its domain, then C has to be a critical number of the function. Now why? Let's just consider that f of C is actually a relative extrema, either max or min, I don't care, and assume also that the derivative at C exists, because obviously if it didn't exist, then it would already be a critical number. There'd be nothing to prove. I'll show you then that the derivative at C has to be 0, forcing it to be a critical number. Suppose not. Suppose that the derivative was actually bigger than 0. That would mean then if you look at the point on the graph for the chosen interval of x values around C, that the tangent line would have to be rising from left to right. Now, but the derivative though is a limit of a certain difference quotient, or at least a rate of change of y's over x's. In this case, that difference would then be f of x minus f of c over x minus c. But if the limit is positive, that means that expression has to be positive. I don't know what it is, but it has to be positive for all numbers near c in some open interval about c. Or the limit could never be positive. It'd have to be something else. But that implies, though, if you focus only on x values that are more than c in that interval, that x minus c would be positive. Well, since the fraction is positive and the denominator is positive, that means the numerator, f of x minus f of c, must be positive. That would imply that f of x is greater than f of c for all x greater than c and near c. Well then, if the function values are always more than f of c can't be a relative max. But if you look at the other portion though, using the exact same argument, I could then show you that f of c could not be a relative min. Well, it's got to be one of them. I assumed it was a relative extrema. Therefore, my assumption that the derivative is positive can't be true. The derivative can't be positive. It must be less than or equal to 0. But I could mimic this argument all over again and show you that the derivative has to be greater than or equal to 0. Well, if both are true, that the derivative is less than or equal to 0 and greater than or equal to 0, then the derivative at c would have to be 0 itself. And that's the proof. So if a function has an absolute extremum, say a minimum, as you could see here in the graph, then that relative extremum, minimum, would have to occur at a relative extremum. And here I've highlighted all the relative minimums. But a relative minimum can either occur at the endpoints, and that means we just gained another point and another x value to consider, or at the interior of the domain. But if it's at the interior of the domain, it must be a critical number. If it's a critical number, the derivative must be 0 or doesn't exist. That means then we'd have to look at all these x values to figure out which one would have an absolute max or an absolute min. That sounds like a lot of work, but remember before we had an infinite number of x values to consider. Now we have a finite number. That's a lot better. So there's a very simple process to find a maximum or minimum of a function, provided we know there is one. So we're going to limit ourselves to those functions that we know have maximums and minimums. We'll deal only with those functions that are continuous on a closed interval, because by the extreme value theorem we know that they have maximums and minimums. So the process is find the critical numbers first. So you need to have the derivative, set the derivative equals 0, and find out where it doesn't exist in the domain of the function. Then we know that among that list of x values, when you include those critical numbers and the endpoints, that one of those function values must be the maximum, because I just showed you that it has to occur at one of those three places. So then the largest such function value out of that list of x values would have to then correspond to the maximum value, and the least such evaluation would then be the minimum. Let's now use that process on an example. So let's go about finding the maximum and minimum of the function f of x equals x cubed minus 12x, where x is restricted to the closed interval from -1 to 5. Now we know that this is a continuous function, and we know it's defined on a closed interval, so we know then that there is a max or a min. The process then to find that max is to first find our critical numbers. So the derivative then would then be 3x squared minus 12. I'll then need to solve that the derivative is 0 for x. But that would then mean that 3x squared minus 12 equals 0. And clearly that means then that x squared equals 4 by solving for x squared. That would then give you x is 2 or -2. But out of them, one of them, -2, is not in our interval, so we ignore it. So the only value we get then for this step is 2. I would then also have to find all x in the domain so that the derivative does not exist. But that would then mean that the expression 3x squared minus 12 would have to not exist. We would have to not be able to evaluate it for some x value. But this is a polynomial. You can evaluate it for any x value. So then you get no steps for that. There therefore is only one critical number, 2. The next step is we now know from what I did that the absolute extrema must occur at the endpoints or at the critical numbers. So all we have to do then is evaluate this function at these x values to find out what the corresponding values would be. So f of -1 would then be -1 cubed minus 12 times -1, and that certainly is -1 plus 12. That would then be 11. And f of 2 would then be 2 cubed minus 12 times 2, and that's 8 minus 24. That would then be -16. And the last one would be f of 5, which would be 5 cubed minus 5 times 12, which is 60. That would then give you 125 minus 60, and that gives you 65. So among these, one of them must be the absolute maximum. One of them must be the absolute minimum. So f of 2, that value, which is -16, that's your minimum value. And f of 5, that being the largest value in this list, would then be 65, and that's your maximum. That's it. That's how the problem is done.